So this is lesson number 6 for Unit 5. I'm actually going to break it up into 2 videos. We're going to save all of the review questions where we're just going to review the idea of area so far, the last few pages of the notes. I'm going to save those for the next video. In here we're going to do 5 pages of notes, and just so you kind of can see how this is going to unfold. The first 3 pages all go together. It's going to look at calculating areas between curves and the x-axis and maybe other curves, right? So that's this page there, and then we're going to do some physics for 1 page, and then after that we're going to look at something called the trapezoid rule. But going back to these first 3 pages, I'm actually going to, right off the start, add in some extra titles here that I think will help you out. This first page here, what we're going to be looking at is what happens when you've got a function that goes positive and then negative and then positive, and it kind of swizzles around the x-axis. So maybe we'll add in an extra little like subtitle here, right? So this is area between f of x and the x-axis. And we're going to have these things that I'm going to call crossovers. These points where the graph goes above and then below and then above the x-axis. So we're going to have some crossovers in there and talk about how the calculus likes to throw negative signs at us for that. Then looking down the road, on the next page, we're going to look at the area between 2 curves. Okay, so you might have one function f of x and then another function g of x. So this is areas between f of x and g of x. But they won't do any swizzling past each other on that page. I'm going to save that for our 3rd page here in the notes. So part C is going to be areas. This is between 2 functions, between f of x and g of x, and this will be with crossovers. So we're going to have crossovers on the first page, but that will be with the x-axis. And then on the 3rd page, it'll actually be with 2 totally separate functions. Okay, well, let's go back. Let's get to this first page here. So I've got a single function f of x, and it's going to cross over the x-axis once or twice during the story. I'm going to play with this particular cubic function here. I've already got it into my calculator. I've typed that in, and I've set my window up to match what's going on the screen here too. And so when I graphed it, I noticed that this graph was positive for a while, and then it briefly dipped into the negatives between 3 and 4, and then it went back to the positives again. And we're going to be taking a look at the story for this graph from 0 out to 5. So at x equals 0, it's just heading into the positives. It's positive for quite some time, and then at x equals 3, it dips into the negatives until x equals 4, and then it goes back into the positives again. Okay, it doesn't really matter how tall you draw this graph. We're just talking about this issue of like, what's our plan when you've got graphs that kind of swizzle around the x-axis like this one. It goes into the negatives and then back into the positives again. And when we go and do our calculus, the calculus likes to tell you that a graph is hanging below the x-axis by giving you a negative value for the definite integral. It's like it's giving you a signed area, like it's saying, hey, this area here is positive, and then it wants to tell you that this area is hanging down below the x-axis. So it tells you, if you can say it this way, that the area is negative. Now, technically areas can't be negative. But we like to think of them as being negative just as a reminder to ourselves that, yeah, that area is hanging down below the x-axis. So, more correctly, we would say, well, the area is positive, but the definite integral is negative. All very nice, but sometimes it's just handier to say, well, the area there is negative. Now, for calculus, if I simply go and ask my calculator to do this definite integral from 0 to 5, it's going to blend all those values together. A positive answer, and then a negative, and then a positive. And it's going to give you some overall addition of positives and negatives. And when you do, it gives you this net area of 175 over 12. I mean, you can try that out on your calculator if you want. Just ask it to do the integral for you. And that's all very nice, but that's blending positives and negatives together. And I'm wondering, like, what if I have to go and paint it? If I'm going to go to the hardware store to buy some paint, and I have to go and paint in here, and I still have to go and paint in here. I don't have negative paint, right? I got to go buy paint for that, and then paint here. How much paint should I go and buy? And in this situation, if I'm going to go and buy paint, I don't want the calculus to throw negatives and blend negatives into the story with me. So in this page, we're going to look at how you can find the actual area, the true area for this. And I want to show you a couple of options. The first one is what you can do if you were to do this by hand without a calculator. So it can be done analytically if you want, right? That just means by hand. So we'll look at that first. I'm not saying it would be quick, but it is possible to do it. Okay, so this just means by hand. First thing you'd have to do is figure out, well, where does this function actually cross the x-axis? You would have to go back up to this equation and say, okay, hey, you are equal to 0, and then solve that equation. That could take you some time. Now, in this picture, I can see that the answer is x is equal to 0, x is equal to 3, and x is equal to 4. You know, you can get pretty quick on this one just by factoring an x out. Then you'd have a quadratic to solve from there. So it's doable, but it might take you 2 or 3 minutes to find those crossover points. Then you could go and ask the calculus to do some definite integrals in sections. You could say, okay, well, from 0 to 3, what do we get? Oops, sorry. 0 to, try this again, 3, and then we'll go from 3 to 4, well, it's always, the function's always in the negatives, and then finally from 4 to 5. And it would take you some time, but it's doable. Analytically, you could do it by hand. You can find an antiderivative, put those values in, and you end up with 45 over 4 for this first one. No surprise that the calculus gives you a negative answer here. It's negative 7/12 for this one here. And then the last one is 47/12. So I'm not at all surprised that the calculus told me that that one integral in the center there was negative. This one right here, it's just saying, hey, this area is hanging down below the x-axis. You know, be aware of that. Okay, that's great, but if I have to go and paint this, I would just want to remove any negatives from that story before I add them all up. So by sectioning this up and compartmentalizing it with the positive and the negative integrals, I can be aware of sections like this that hang down, flip them over to becoming positives, right? And then add everything together. And I can come up with the paintable area if I had to go and paint this thing. And when I do that, it ends up being, well, it ends up being like 189/12, which I think actually reduces to 63/4. Now, what's worth pointing out is, you know, take a look at that 189/12. This number here is larger, right? It's noticeably larger than the original number at the top of the page here, where we had that 175/12. So the calculus up here was blending those answers together, and the negative was hiding some of that area from us. So if you really want the area, you could do this by hand, but you'd have to section it up, and it would take you quite some time to do it. There's a faster way. You can do this numerically, right? You can do it with your calculator. Actually, I want to show you a couple of options for that. First thing you could do is you could try graphing the absolute value of the function. Now remember, this function dipped into the negatives between 3 and 4. And what I could do is say, hey, calculator, I don't want to see that function there. I actually want to see the absolute value of it. So maybe I'll just deactivate this one for a minute. I'm going to go down to Y2 and say, hey, I would like to graph the absolute value. So that's under the math menu. I slide over to number. It's the very first one. And I want to do the absolute value of Y1. So I hit the vars button, Y variables, function, and number 1. There. This will now instead graph the absolute value of that first function. So the little dip that was supposed to go into the negatives between 3 and 4, you can see that little bump here. Now it actually goes into the positives. All right, so great. I've got this picture now of the absolute value of the function, right? This section kind of looks unchanged, but then this little dip flips into the positives, and then the graph goes up like that again. Now everything is positive, right? So I can just do this by asking my calculator, hey, calculator, what are your thoughts on this question here? Let's integrate from 0 to 5, but let's integrate the absolute value of that function that we had. It might take my calculator a few seconds more to do it, as it does all of that absolute value calculating, but I think it can now get it right. So if I say, hey, calculator, let's calculate an integral, number 7, from 0 to 5, it'll think about it for some time, and then it will shade in this area, and all of this area that it's shading in, it will consider positive, for the definite integrals. So when it finally gets around to drawing this, it's actually going to give me the right area for the answer here. So even this section is positive, and it says, okay, there's the number that I've got for you, which, by the way, is the 189/12. So it is actually doing this right. Okay, so that's great. It's more than that 175/12. Now, if you don't want to spend the time drawing the graph, and you just want to really quickly come up with an answer, you could have just gone to that numerical integration option, and then said, hey, I want to integrate the absolute value. I've got an old TI-83, right? So it's going to look like this. And then I could put my function in there, right? I could put my f of x in there, and then I would go x, 0, 5, right? I can do that all in one shot. There's the TI-84 option as well, right? You can just say, hey, I want to go, and well, the TI-84 option will look remarkably similar to this right here, right? So just do that on your TI-84, and it will be very, very happy and give you the right answer of the 189/12. Now let's back up a little bit and take a look at what we've just done, because there are 3 pages here and they're all kind of the same. So on this page, we only had one function, just this f of x, but this one function was swizzling around, crossing the x-axis, sometimes with definite integrals being positive, sometimes with them being negative. And what we found is, well, there is a way to deal with it. There is a way to come up with the true area between the graph and the x-axis when it's doing that swizzling. The next page doesn't have any swizzling as such, non-technical term, but it does have a couple of functions, okay, 2 separate functions. I'm going to call them f and g, and you can see them right here, x plus 8, and then 1/2 x squared. In fact, I'm going to go and put these into my calculator here. All right, so putting these in, first one here is x plus 8, and then the next one is going to be 1/2 x squared. Okay, so x plus 8, oh yeah, okay, nice line there. Slope is 1, y-intercept is 8, and then a parabola that's heading up towards it. Okay, fantastic. So I'm just going to sketch these really fast here. I'm not even going to pay too close attention to where all the points should be. Like I guess it's roughly going roughly like that. Right, there's f of x, roughly. And then the g of x, it's this parabola underneath it, doing something kind of like that. And what we're going to do now is try to find the area between the curves. Starting in this story, it looks like at x is equal to 1 and stopping at 4. So that was decided for us, right, that we would begin here and stop there. It's like, oh, okay, sure, if that's what you like, right? So there's a nice little boundary. And what we're going to try to find is how much area would there be in between those graphs if you had to paint them? Well, right now we know that the definite integral finds the area between the graph and the x-axis. So here's the plan. We could imagine just 2 separate stories. You know, as you're doing your little Riemann ribbons here, you could have some ribbons that are going all the way down to the x-axis, and they're figuring out how much area there is under that. I've drawn it in blue, f of x, all the way down to the x-axis. And then you could do a whole new summation of all of these little ribbons all the way along. And then you could figure out, if you subtract those 2 answers, how much area there is in between those 2 graphs. Right? So your goal is to come up with a plan here to be able to go to the hardware store and buy just enough paint to do this, to paint in between those graphs. Right now, those 2 graphs are not swizzling through each other. That's going to be on the next page. So, nice simple option. You could just say, hey, look, we've got to integrate that tall function there from 1 to 4. We're going to integrate f of x dx, and then we will just simply subtract the area that's between g of x and the x-axis. That would certainly work. And you're very capable of doing that, so I'm going to save you some time and just tell you that when I tried this out, I had 31.5 for that area under the blue graph all the way down to the x-axis, and I had 10.5 for the area underneath that green graph, the parabola. So the final paintable area, if I had to go to the hardware store and buy paint, is 21 units of area. And that's great, right? That's the right answer. That's going to be our plan. Now, a different way to look at that, it's really the exact same math. You know, mathematicians would say, hey, you're not saying anything new when you say this. But I just want to show you a different way of thinking about what we've just done. Just going to draw those same graphs again, something like this. Instead of subtracting after you've integrated, you could actually imagine subtracting the functions first, right? You could subtract. My suggestion here is you could even go and graph this difference. I'm not going to go to that much trouble, but you could subtract one function from the other to find out how tall these red ribbons are, and then say, hey, I have to add those red ribbons up, starting at 1 and finishing all the way down at 4. And if I add up all of those ribbons, that should tell me the area as well. So here's a different option. Comes up with the exact same answer. It's mathematically really not all that different, but you could say, hey, I could go from 1 to 4, and I could integrate, I could add up the area for f of x minus g of x, right? The tall function minus the short function, dx, right? I could do the subtraction first and then do the integration. And it works beautifully. If you try that out, you end up with 21 units. So it's just a different way of looking at the exact same question. Okay, before we go to the third page, where we're going to have graphs like this, the blue and the green, f of x and g of x, that swizzle by each other, let's try a nice little numerical one out. One that's just so awkward, we're going to need to use our graphing calculator to help us out. So we've got 3 functions that are actually kind of deciding some boundaries here for this shape. One is this blue graph of 6 root x. And then we've got this exponential, which I've kind of gotten in that teal color there, 2 to the x minus 1 minus 3. And then another part of the roof at the top is 10 minus 2x. I guess it kind of goes without stating that there's a bit of an edge here over there. I'll just kind of draw it in pink, right? Otherwise, those blue and the teal graphs, I don't think quite touch each other there. And somebody's asking us, can we go and find the area for that story? And the answer is sure, but there's one catch. This thing seems to do a switch, and for a while, from this marker all the way out to this spot, which is not really a very nice x value, it looks like it's that blue graph on top and the teal one on the bottom. Then, for the next little while, it goes red graph on top and the teal one on the bottom. So what I might need to do is figure out the x values for these locations. This one's 0. I'm just going to call this one here capital A. And even on your AP exam, you can do that. You can say, I'm declaring this spot, this value to be called capital A. And then I can go and just say, yeah, now I'm integrating from 0 to A. So I'm going to go and find those values right now. I'm going to go and see what A is and then what B is. And I am definitely going to use my graphing calculator to help me out with this. So I'm going to put these into my graphing calculator here. Clear these ones out. Okay, so in no particular order, I've got 6 root x, and another graph is this teal one, 2 to the x minus 1, then take away 3, and then the last one looks like it's 10 minus 2x. Okay, didn't really put those in any logical order at all. So I've got that one, and then my second graph is this one, and then my third graph is this red line. Well, I want to know the intersection x values for this point and this point. So I do need to know which one I've called which. The last one coming in for me, number 3, was this diagonal. So I might say, hey, calculator, can we calculate an intersection? Now, there are 3 graphs on the go, right? So it's asking me, well, which graphs do you want to work with? Well, right now I want to do that 6 root x and then the 10 minus 2x. So I'm happy that it's saying, do you want to use that one? I just say yes. And then it says y2, do you want this one? No, actually I don't. So I'll hit the down arrow. Yeah, that's my other one. And a guess, well, that's probably close enough. So it says, okay, that point is 1.4222. Now, I'm going to write this down, but if I'm writing my AP exam, I'm going to want to have that super precise when I go to do my work. So I'm going to just store that. I bet you right now, if I quit this screen, it's probably stored in X. Yep. Now, it's not going to stay there very long because my calculator feels like it's welcome to change that value in X. So I'm going to say, hey, can you make a copy? Can you store that into A? There, it's now got it in A. Okay, back to the graph. Let's do another intersection. calculate an intersection, number 5, between, I want to do the 10 minus 2x and then the exponential. So not this graph, but yes, that one and that one. And that's probably even close enough. I can probably just say go. I think that'll find it. Yes, it did. So it's at like 3.557193. I'm going to quit this screen, double check that that's sitting in X. I believe it is. Yes. I'm going to store a copy into B. Done. I've got copies now ready to go. So if I was writing my AP exam and they're saying, hey, go find that area, I would just do this. I would just say, well, that area is going to be, and I have to show them what I would do, right? I'm going to do a definite integral from 0, and I'm allowed to say A, as long as I have earlier shown them, like this is what I mean. A is that intersection point. And I'm going to integrate one function minus the other. I'm going to try it out the way I had up here in red, right, where you go f minus g. So I'm going to go 6 root x, and then subtract this exponential. I better put that in brackets. 2 to the x minus 1, take away 3. dx. Okay, that's part of the area. Then I'll add on some more. I'll say I now have to integrate from A to B, and now the thing on the top is 10 minus 2x. Subtract that floor on the bottom, 2 to the x minus 1, take away 3. I do need those brackets just to make sure everything's kind of got the right flow to it. I'll let you try this out on your calculator. Those can be done now on your calculator, and you can actually say, like, yeah, let's integrate from A to B, right? It's totally that option. If I know which one's which, okay, I'll remember that. I could even do this. I could say, okay, calculator, let's do a numerical integration, and I'm going to go with this one minus that one. So for me, that was y1 minus y2. I'm using x's, and I'm going to go from 0, and I can just go to A, and it'll figure it out. It'll take it some time, but it'll figure it out. And I might even just say, all right, let's go and add another story onto this. I'm going to go and add to that. Did I just do the wrong thing here? Sorry, this should have been, my bad. I hit the wrong button. This should have been not number 8, but number 9. I want to do numerical integration. Sorry about that. Let's get it right this time. A numerical integration, and this time it's going to be y3 minus y2. At least that's the order that I type them in. And I'm using x's, going from A to B. And it's probably going to take a really long time to do this, right? Because it's going to chug away on each one of those. Each one of them takes it a certain amount of time. TI-84 would probably be a little bit quicker. I know what the answer is supposed to be. It's around 20.4, so let's see if I've typed this in correctly. If I didn't, I'll have to go back and find the error. Yep, that's the right number. Okay, so 20.4049. So yeah, you can do those numerically. Feel free to use your calculator to do that. Now, the third and final page for this set of 3 pages, I'm going to go back just to kind of look at what we've done. First page of the day was a single graph that was swizzling, right, with the x-axis, right? Just one graph though, just an f of x. Then we said, well, you could do 2 graphs, right? You could just take one and subtract the other. And now we're going to do 2 graphs that swizzle. So don't worry about the x-axis so much, but we have 2 separate graphs here, and we're going to try to find the paintable area in this story, starting at 0 and finishing all the way at 5. And so you have to be super careful, because if we're not, the calculus might say, oh, well, that area here, maybe that's positive. And it might say, well, this area is positive. And the way we set up our calculus, it may say, oh, well, the definite integral in here is negative, right, depending on how we set it up. And we might not want that to happen if we have to just go and paint the whole thing. So I want to show you a plan for finding the paintable area, the true total area, not the kind of calculus net area. So if you have to do it analytically, if you have to do it, by hand, yes, it's possible. But the first thing you'll have to do is figure out where those functions cross. So you would have to take this algebra and set it equal to each other and then solve. And it might take you some time. But in this story, it ends up being an intersection at this point and at that point, at x is equal to 1 and at x is equal to 4. Now that is not a quick process, right? That could be a 3-minute thing to take those two functions and carefully figure out where they're equal to each other and solve for all the x values where that happens. But that is something that you could do. And then you could integrate in sections, right? One function minus the other. Now, in this particular story, the f of x was the linear one, so that's this one. It's on the top at the beginning, then it goes under, and then it goes back to being on top. And then g of x is this one down here. Okay, now you'll notice that when I have gone to integrate with these sections, I'm not even really worried about which one's on top. I'm just going to remove minus signs anyways. So I might just go, oh yeah, f minus g, and I'll integrate from 0 to 1, the first crossover point, and I ended up with 11 over 6, because f was on top there. And then I'm going to integrate from 1 to 4 between these two swizzling x values here. And when I do that, because f is actually under the g, the whole time I'm integrating negative upside down ribbons, so I get this negative answer. That's okay though. I knew some of these might come out negative. I guess what I'm saying is I'm not going to bother worrying about which one should be subtracted from which one. I know that I can just remove minus signs later. It's not a big deal. And then I can integrate from 4 to 5, which apparently was where we wanted to stop. And when I tried that out, I got another 11/6, just like the first one. So you could do this by hand, and then you could just remove any negative signs. You could say, oh, I'm going to call that a 9 over 2, right? And then add on the next 11/6. Completely doable, and you end up with the right answer here. That is 49/6. Okay, that can also be done on your calculator. Okay, so that's what we mean by numerically. What you would do is you would tell the calculator, hey, I don't ever want you to have a negative when you subtract. So you could say, calculator, would you do this for me? Can you integrate from 0 to 5? And then what you want to do is, sure, we're going to actually go and we're going to have an f of x minus g of x in here. But I want to put some absolute value signs on this, absolute value bars. And I don't want to put them on each individual function. Instead, I want to put them on the whole subtraction. So the subtraction is accomplished at every rectangle, and then you remove any negative signs. So it has to be like that, not on the individual functions themselves. And if you try that out, it works beautifully, right? So sure, you could even put that into your calculator if you want, right? It could be an option. Okay, you could put that into that numerical integration feature, and it'll give you that 49/6. So that one's kind of like the first page, but instead of being a function in the x-axis, it's actually two separate functions. I guess you could say the x-axis is kind of like y equals 0. So in some sense, the first page is just like this one, except right here we've got, like a 0, right? Like y equals 0 for the x-axis. Okay, 2 more pages to go for this lesson. Going to switch things up here a little bit now. For page 28, we're going to talk finally about the physics world in like the full sense. We're going to get everything dialed in together. And so on this page, just kind of looking at the whole page here, there are a lot of different graphs. And each one of those is some sort of physics story. And then the red and the green arrows are some relationships between them. And I just want to, on one page, finally tie everything together so you can see how each one of the physics words gets tied with each one of the other physics words. And it's actually been a kind of a long wait until now to finally get everything exactly right. So I've got the story that the velocity is 6t squared minus 42t plus 60, and it's going to go from 0 to 6. Well, that's a parabola, right? It's degree 2. That's actually this picture halfway down your page on the left. So here's the velocity. It is 6t squared minus 42t plus 60. Now, how do you move around from one graph to the next? Well, there are some options. If you want to go back up the page and get to position, which is what's going on up here. This is S of t. To get there, you can do that, but you'll have to do an antiderivative. So in this case, you'd be saying, okay, I have to go and do an antiderivative of this story down here. And so if you do that, well, it's going to be something like t cubed. Now let's think this through. A 3 would come down. I think that would need to be 2t cubed in order for that to work. And then this part here, this is going to be, what, 21 t squared? Yeah, that would be a minus 42t plus a 60t. And then there's an arbitrary constant that people would have to give you some information to go and find. There's no way to know it unless they help you out. So that's how you could get back to position. If you had position, you could take a derivative to go down the page to get to velocity. Okay, well, before we've talked about how you can get to acceleration. So if you have velocity, you can do a derivative to go down the page here to get to acceleration. Or if you have acceleration, you can do an antiderivative to go back up the page. But yeah, the acceleration graph would be this one here. It's actually a pretty simple graph. By the time you do a derivative, the acceleration here would just be 12t minus a 42. Okay, great. So that ties together the first 3 stories there: position, velocity, and acceleration. They're just tied with derivatives and antiderivatives. Now, my claim is, if you want to get to these other graphs over here on the right, there's no link between the upper 2 graphs. The only link is to go over with some sort of process, and then maybe you can do derivatives and antiderivatives over here. And this process right here is absolute value. And if you do the absolute value of velocity, then you can get to speed. So speed is the absolute value of the velocity graph. That's how you draw the speed graph. If you take the speed graph and if you integrate it, if you do an antiderivative, then you can find the distance that you've gone. So distance is actually the integral of speed dt. It's the integral of the absolute value of the velocity. If you take a derivative of that, then you'd be talking about speed. So that's the tie between all of those. And you can see the tie between velocity and speed is not too complicated, but there's no easy tie between position and distance that you've gone. You actually have to kind of work your way over through speed first. Now down at the bottom right-hand corner, let's throw in the last word that physicists like to throw in there every once in a while. They say, oh, what about the displacement of the object during the 4th second? Well, the 4th second, that would be, if the first second goes from time 0 to time 1, the 4th second would be from time 3 all the way out to time 4. If you want to find the displacement of the object just during the 4th second, what you can do is you can integrate just from one time to another. You can integrate velocity, and that'll actually give you the displacement. So here you could actually integrate from 3 to 4. You could integrate that velocity machine. 6t squared minus 42t plus 60 dt. And it ends up being negative 13. So it's kind of neat that the calculus does give you these negative values for definite integrals. It's perfect for physics because it'll actually tell you that, oh yeah, during that 1 second you actually move backwards by 13 units. Okay, well that finally ties the whole physics story together. Now let's go and take a look at one last page. We're going to look at something called the trapezoid rule. And then once we've got that dialed in, then we're going to look at how you can estimate some errors if you're doing Riemann sums. Have this graph here of just negative x squared plus 2x plus 9, and I'm going to try to think about the area from 0 out to 4. But instead of doing like a left attached or a right attached, because I know we've done that, so let me just drop these in for a second so I can play with them for just a minute. Okay, so I'm going to make these red, and that's kind of messy, so let's Add some transparency here. Okay, that might be a little too transparent. There we go. Okay, so we talked about taking ribbons. Maybe I'll move it over here. We've talked about taking ribbons and maybe left attaching them and maybe right attaching them. Well, here's another option. Instead of doing that, which can give you a lot of error, I guess you could do, 1, 2, 3, 4 big ribbons here. Let's try something different instead. What if we were to fill in the area underneath with trapezoids? That could look kind of neat, right? They would actually look, I guess, kind of like this, right? They would go up. I'll draw one in over here. They would have that shape to them. They would have two parallel sides and then, two different heights to them, right, for those parallel sides, and then a diagonal top to them. And then we could say, okay, well, what's the area of that? And if we filled this whole thing in with trapezoids, that could actually be pretty darn accurate. And this is just called the trapezoid rule, right? What you're going to find is that you're going to use every single one of the fence posts. Okay, so we have in this story 5 fence posts, and we're going to need to know all of those y values, right? So there's a fence post here, and here, there, and one last one there. The actual y values are, looking at them here, we've got 9, 10, 9, 6, and a 1. I'm actually going to use them all. I'm going to start off by not doing the trapezoid rule, but just doing an LRAM. What if I attached all of these ribbons on their left side? I could put a ribbon in here, there, and then I'm going to undo that feature pretty quick. And then one last ribbon here, and if we're attaching on the left, I would never need that y value of 1. And so my area estimation using LRAM would say, okay, we're going to go 9 times 1 wide, plus 10 times 1 wide, plus 9 times 1 wide, plus, and then the last one would be 6 times 1 wide. And that ends up being 34. Okay, well, what if I want to go and do right attached? The area estimate then, my first ribbon, if I attach on the right, is going to look like that. And I would say, okay, attaching on the right, we're going to go 10 times 1, plus 9 times 1, plus 6 times 1, plus 1 times 1, and that ends up being 26. A quick way to try to figure out, well, not to try, but to actually figure out how much area you would get with the trapezoid rule is to actually just average LRAM and RRAM. It's the nicest, quickest way to find the areas of all those trapezoids. So I'm just going to put in here, it's just the average. So all you'd have to do here is just take those two answers, add them up, and divide by 2. So, okay, 34 plus 26 divided by 2. And in this case, the area prediction is 30. And it's usually a lot more precise than the LRAM or the RRAM. Again, quickest way, instead of trying to figure out the actual formula for the area of a trapezoid, is to just do an LRAM and then to do an RRAM. Usually we're pretty quick at those, and then you can average the two. I mean, you certainly can go and add up the trapezoids, but most people spend more time doing that than they would if they just did LRAM and RRAM and then adding them up, dividing by 2. Okay, we have to be aware, last thing for this lesson, of estimating errors, knowing whether your LRAM or RRAM or your trapezoid rule is going to under or overestimate the true answer. And it really depends on some qualities of the function. It might be whether it's increasing or decreasing, or it could depend on its concavity. You will get an underestimate of LRAM every time you play around with a graph that's increasing. So let's just draw a graph that's increasing. And if you were to go and add in, I'm going to go and sneak up here and grab a nice little copy of this. If you were to go and add in ribbons that were left attached, what you will find is that this will always underestimate the true area of the graph if the graph is increasing. So if you're ever dealing with a situation and they say, oh yeah, this function is increasing, please do an LRAM, and then they ask you, do you think this is an over or an underestimate? You can say it's an underestimate. And if they say, well, why? Why do you know that? You can say, because the graph was increasing. So an increasing graph will be underestimated by LRAM. How do you underestimate an RRAM situation? The other way around. If you're playing around with a graph that's decreasing, then if you do an RRAM, you will always find yourself underestimating the true story because it's going to attach like that. So if they say, all right, please do an RRAM for this decreasing graph. Hey, what do you think? Is it over or underestimating it? You can say, look, it's going to underestimate it. And they say, why? You can say, because the graph is decreasing. But for the trapezoid rule, it's not about whether the graph is increasing or decreasing. You will underestimate the true answer for the area using trapezoids if the graph is concave down, if it looks like that. So it's not about increasing or decreasing. That doesn't tell you whether you will over or underestimate with trapezoids. Actually, I can't use that because that's not going to draw a trapezoid. I'm going to have to draw this one by hand. So if I put in some trapezoids here, maybe I'll do 2 trapezoids with 3 fence posts. These trapezoids are going to underestimate the true area. And if somebody says, what was it? Why do you know this? How do you know this to be true? You can say, because you told me this graph was concave down. Now the opposite. In which situations would you find yourself using these rectangular or trapezoidal approximation methods? When would you find yourself overestimating the true answer? Well, the exact reverse. If you've got a decreasing function and you try to do an LRAM, then you are going to overestimate the answer. Your area estimate will be too high. Okay, so that happens for a decreasing function. You will get an RRAM overestimating the true answer if you have an increasing function. And final one. In what case will the trapezoid rule do an overestimate? It's not about whether the graph is increasing or decreasing. It's about whether or not it's concave up or concave down. And a concave up graph will be overestimated by the trapezoid rule because the trapezoids will stick up above the graph like that. So the issue there is about it being concave up. Now the remaining pages are just some review, kind of looking at the idea of area so far. Just about 3 or so different old review questions. I'm going to save them for the next video. So we're going to stop this video right here at this spot.